Hello everybody, my name is Daniel Silver and today I'm going to be talking about our work MosaiQ, Quantum Generative Adversarial Networks for Image Generation on NISQ computers. Quantum machine learning has a lot of potential and has recently been getting more and more attention. Back in 2017, in a Nature article published, they proved many theoretical advantages for many quantum machine learning algorithms. In 2018, more recently, an article published in Physics Review Letter proved theoretical advantages for quantum generative adversarial networks. So why are quantum computers so powerful, and specifically why are they so powerful for machine learning tasks? Well, quantum computers exhibit many properties that can give them potential benefits over their classical counterparts. And when we say benefits, we mean computational efficiencies. One of the properties that enables this is superposition. To understand superposition, we have to understand a little bit about the qubit. So where a classical bit can exist in either the 0 or 1 state, a qubit can exist in a superposition of these states, a sort of combination that where the output could change based on when it's measured. We also have entanglement, which creates rich interconnections between qubits, forming an interdependent system where one cannot be fully described without describing another qubit. This lets the qubits work in these together let the qubits work in a very high dimensional space, uh, which is very efficient for many machine learning tasks. We also have interference, which is a very useful property for certain quantum machine learning algorithms. So classical image generation using GANs. So a GAN is a generative adversarial network, which consists of a generator and a discriminator that are trained simultaneously in a competitive process. The generator works to create fake data samples, while the discriminator works to distinguish the fake generated images from the real images. In order to do this, the generator receives random noise as an input and creates an image from that noise. Whereas the discriminator is a classifier circuit. It either takes real images from the actual dataset, or it takes generated images from the generator, and it decides whether or not the images came from the real source or from the fake source. And together, this adversarial process creates very high quality images. So quantum GANs. So many approaches for a quantum GAN leverage a hybrid configuration with a quantum generator and a classical discriminator training simultaneously. A technique that's often used is called patching for the generator, where multiple subgenerators work together to each generate parts of an image or part of the features being generated. Down here we have the ansatz, or the circuit structure for a quantum generative adversarial network. The rotation gates, the Rx and Ry gates, can form the basis of the optimization, where these can be tuned based on the objective of the learning. The Z gates you see here are fixed structures that create entanglements between the different qubits, so they can operate in a high dimensional space and form this interdependent system. Together, at the end, these get measured and the outputs become part of the image. So here's some of the results for our approach MosaiQ. So by employing these techniques, we find very high quality image generation compared to the previous state-of-the-art QG patch. We can see in the cases of the digit 0, 5, 9, in addition to images such as boots, t-shirts, and trousers, MosaiQ produces higher quality images that are more resembling of the input data set as compared to the previous state-of-the-art QG patch. Additionally, we perform more of a quantitative analysis here, where we look at the FID score, which a lower FID score is closer aligned with a higher image quality. So we find that over all the MNIST digit classes and over all the fashion MNIST classes, we observe a lower FID score compared to the previous state-of-the-art, indicating higher image quality in all of these cases for all the distributions. We also examine the results on a real quantum computer. So we test the performance on a real quantum computer exhibiting noise, IBM Jakarta. And we find overall we maintain higher image quality over the state-of-the-art when testing on a real quantum computer in a noisy environment. And we find this holds true for all the classes tested as well, with visual indications as well that these images are of higher quality even when noise is present. Thank you so much for listening to this brief talk. To learn more about our technique, come to our poster session Wednesday, 2:30 at the Image and Video Synthesis 1. You can read our paper MosaiQ here, or download the code here. My name is Daniel Silver. It's been a pleasure. You can find my email here, and I look forward to hearing from you or seeing you at the poster session. Thank you.